In this video, we'll dig deeper into the mechanisms that allow the distributed nodes of a IBM blockchain network to maintain a consistent ledger state. Let's start by looking at how a consensus mechanism is used to maintain a consistent ledger. The idea here is that you have a network of validating nodes, and they each will execute a particular smart contract, and then they'll compare their results. And if you reach enough consensus within this network, then you can be reasonably assured that this is actually a correct transaction, and then you can update the world state to reflect the results of this particular set of transactions. So while we're not going to get into the actual theory behind particular consensus algorithms, we can say that in order for consensus to be reached, there are three characteristics that must be true. The first one is known as agreement, and this just means that all correct processes or nodes within the validation network have to agree on the result. So they all have to come up with the same answer, which is fairly intuitive. The next characteristic that needs to be true in order to reach consensus is what is known as termination. And this just simply means that all correct processes or validation nodes need to actually terminate with a result. And last but not least, the third characteristic that has to hold in order for consensus to be reached is what is known as validity. And in particular, we need something called strong validity in order for the consensus mechanism to be fault tolerant. In layperson's terms, strong validity really means that within the network, a given correct process or node will have validated its result against the results of all other correct processes or nodes in the network. So in other words, if you're a validating process or node and you come up with the answer X, you will have also validated that all the other correct processes or nodes in the network also came up with the value X. This is done during the running of the consensus algorithm and achieved via message exchanges. And that's why, again, these networks are all point-to-point. So every validating node will have a direct connection to every other validating node. Let's look at an example. On the left, there's a network with 4 nodes. The green indicates a node in good faith, and red indicates a bad actor. On the left, we see we have 2 green nodes A, B, C, and 1 green node D, E, F that's either mistaken or defective. Once consensus is run, all the good actors agree, and the bad actor, JKL, is effectively quarantined. So this type of consensus keeps all the peers up to date. It'll fix any peers in error and will quarantine any malicious nodes. And there are different algorithms or implementations of consensus that can be plugged in and configured per deployment. So with that short primer on the theory behind consensus algorithms, let's look at the big picture of how consensus works within the scope of an entire network. In the center of the diagram, these round objects represent peers in the consensus network. Now, the actual number of pairs and their various roles are actually determined by the specific algorithm that's used. By default, PBFT is used, and PBFT stands for Practical Byzantine Fault Tolerance, which is again a consensus protocol, and again is the default in IBM blockchain. Within PBFT, there are certain types of nodes. In particular, there are validating leader nodes, there are validating nodes, and non-validating. But suffice to say at this point that we have our consensus network with nodes, we have applications that invoke smart contracts, and then we have the smart contracts themselves that are deployed to and executed on the peer nodes. As we talked about in a previous slide, the consensus mechanism uses messages between the peers in order to achieve consensus. Now let's go into more details about how PBFT works. Again, PBFT is the default consensus mechanism used by IBM blockchain, and it has various stages. So the first stage is submission. But before we get into details of submission, let's look at the types of peers in a PBFT network. So there are three types. There's a non-validating peer, there's a validating peer, and a validating leader. The non-validating peer runs the REST services that external applications will connect to. So they will actually construct the transactions and then forward them to a connected validating peer. The non-validating peers also host the event streams so that external applications can monitor and react to specific events. The validating leader and the validating peer comprise the consensus network, and under the direction of the validating leader, the validating nodes will run the consensus algorithm and stop when consensus is achieved. Now let's look at the details of submission. As you can see from our diagram, we have three sets of transactions being submitted to the network from various sources. These are being submitted to non-validating peers and then being passed on to connected validating peers or validating leaders. It's important to note that because of the distributed nature of the network, the transaction sets may not arrive at the validating nodes or validating leaders in the same order in which they were submitted to the network. So one of the things that we need to do in subsequent steps is to make sure that all the validating nodes actually agree on the correct order for these sets of transactions. But at this stage, we're just showing you the arrival of the transaction sets and then the forwarding to the validating leader and the validating nodes within the consensus network. So the next stage in PBFT is ordering. As we mentioned previously, the transaction sets can arrive at the validating nodes in different orders depending on where they were submitted from and when they were submitted. The very next stage after submission is actually ordering. And what happens here is that consensus is used. The consensus network is used to agree upon an established order. So the consensus protocols that we talked about earlier and the mechanisms where messages are exchanged until a consensus is reached are actually run to determine the correct order of the sets of transactions. And of course, it's not hard to see why ordering is important. For example, in an asset management scenario where multiple transactions involve the same asset, it would be pretty important to get the correct ordering right. The next phase is the execution phase. During this phase, as you can see, the validating peers and the validating leader will execute the smart contract code against their local copy of the ledger and their local copy of the world state. It's important to note here, because this smart contract code gets executed multiple times for the same transaction, that any external calls need to be repeatable. The final stage is validation, and during this stage the consensus protocol is run in order to reach agreement as to what the final changes should be, and once there's agreement reached, those changes are actually committed to the public ledger and to the world state. A special hash called a delta hash is used to validate that the various participants in the consensus network actually do agree on the same end results for a given set of transactions.